Okay, this is take number 2. So I already have some stuff written on. Now, what I did was I have this written in my notebook, and I took pictures of it thanks to my iPhone, and I made it into a PDF. I'm gonna go a little quick because it is getting late and my kids are getting tired and fussy. So, in behavior, this is what happens at the end of the x-axis. So if you draw the x-axis, 0, 1, 2, 3, 4, etc., positive infinities over here, negative infinities over here. These are the ends of the x-axis. So that's what we're talking about when we talk about end behavior. What happens as x approaches positive infinity, and what happens as x approaches negative infinity. Then we have something we've already talked about, zeros and multiplicities. So that that is going to be a concept that's continued for polynomials that are not just quadratics. And then solve applied problems. I'm not sure how many we're going to do of those. 4.2, very much, you have to know 4.1 in order to get to 4.2, and they overlap in the graphing section. Intermediate value theorem, I think I actually have a handout for that, so but we're not covering any of this right now. We're going to just do 4.1, focus on 4.1 right now. So I'm going to grab another color, and vocabulary. So vocabulary, you actually already know some of these because I've been using them, but you have a polynomial function, the degree of a polynomial, the leading term, leading coefficient, zeros, multiplicity. Intermediate value theorem is a vocabulary word, but it's not going to apply to what we're doing right here. So type of function is what we're going to look at, and then we're going to have an example. We're going to... Hi, little baby. That's little baby. The degree of the function, the degree is your highest power, okay? Your highest power is the degree. Your leading term is the coefficient, and your variable. Your leading coefficient is just the coefficient on that term. 1 second. Little baby, you're going to have to calm it down. Hey, shh, here, can you have this? Okay. Now, the first type is a constant type. The constant polynomial function looks like this. Just f of x equals 3. It's just a constant number 3. Now, remember, x to the 0 is the same thing as 1. So we can write 3 as 3 times 1, 3 times 1, which can be written as 3 times x to the 0. So when you're looking at a constant function of 3, your leading term is 3. Your leading coefficient is, see, that's not really appropriate here. It's more of an NA at that point. But your degree is 0, okay? The second type, let's look at this example. I'm going to switch colors. I'm going to look at what is the exponent of this x. The exponent of this x is 1. And I see no other variables, no other x terms. So the degree of this polynomial is 1. You know what I'm going to do? I'm actually just going to go straight down this list, and I'm going to look at the degree, the highest power of each of these functions. So I look at this next function. It's a quadratic. Here we have x squared, x to the first power, and technically x to the 0. Our highest power is 2, so that would be my degree. Here, highest power, 3, 2, well, it would be 3 right there, 3. Then our next one, we have x to the 4th, x cubed, x squared, x to the first power. Our highest power would be 4. So now the words that go along with these, if you have the highest power of degree 1, that's a line, right? Y equals mx plus b. That's a line. So this is a linear function. Our next, 1 second. Go. Now, I've already told you to take that water hose away. My goodness. Okay. So we if our degree is 2, we have a quadratic. If our degree is 3, we have a cubic. A degree of 4 is a quartic. And degree of 5 is a quintic, but we don't have a degree 5 example here. Our leading term. So the leading term, I'm going to change colors. I think I like that. Our leading term is the entire term with your highest power. Okay, so here our entire term is 2/3 x. Our leading term, highest power is 2. Our leading term is 4x squared. Our highest power is 3. Our leading term is x cubed. Our highest power is 4. Our leading term, negative x to the 4th. The leading coefficient is just the number in front of those. So I'm going to pick, I don't know, maybe I'll pick a purple. Our leading coefficient is just the number in front, okay? That purple's kind of similar, so maybe I'll switch to this purple. Just the number that's in front. So here, our leading coefficient is 2/3. Our leading coefficient is 4. Our leading coefficient is 1. Our leading coefficient is -1. So it's really, really pretty simple. That's just giving you an example of what all of those vocabulary words are. Now, the domain of a polynomial, for every single polynomial, the domain's the same. It's negative infinity to positive infinity. It's all real numbers. Negative infinity to positive infinity. All real numbers, okay? It goes on forever to the left, and it goes on forever to the right. Now, let's look at some non-polynomials. This is an absolute value. A poorly drawn absolute value, but an absolute value. This is a square root function, okay? This is here, if I wanted to dot in before a transformation, okay? This is the origin. This is where the origin would have transformed to. Here, this is called a cusp. You see how it kind of looks like 2 fingers pinching together? And you're squeezing it together to a point. That's a cusp. And that's really important in calculus because it's non-differentiable. And then you have your rational functions. And your rational functions are created from polynomial functions. So they are, they're very nice and pretty as well, except for at those points where the values are not in the domain, right? Where you have that vertical asymptote. Anyway, so that is page 1. I'm going to attempt to try to do page 2 of these handouts. I don't know how well it's going to work. But the leading term describes the end behavior. So remember, the end behavior is at the end of your x-axis, right? End behavior is at the end of your x-axis, where x is going off to positive infinity and negative infinity. So here, what that means is if I have my graph, right? It doesn't matter what's happening for small x values. It matters what's happening at those arrows. And that's why we draw the arrows with little dots in between, okay? So if you think about x squared, positive x squared, is a parabola that opens up, right? Positive is a happy face. Well, this is actually the same if you have any even power of x. So this would be positive x squared, positive x to the 4th, positive x to the 6th, etc. Doesn't matter. Now, if you have negative x squared, negative x to the 4th, negative x to the 6th, what does it look like? It looks exactly like negative x squared for the end behavior, okay? The stuff right there in that little mountain, well, you don't really know what happens. You don't know what happens for higher powers. You could have something that looks like this. Whee! Okay. Now, what's happening there in that ... What's happening there? That helps you to determine what power you're looking at. Because we know this is not x squared, right? This is not a negative x squared. And I know this is not a negative x to the fourth. I can count 1, 2, 3, 4, 5. And I can tell you the minimum exponent just based on that. Okay, so we're going to get there. That's what we're looking for. That's where we're headed. Okay, so now let me draw a line. Whee! So this is for even. These are for odds. X cubed, one side goes up, one side goes down. Same thing for any x to the odd. One side goes up, one side goes down. If it is a positive, now let me show you this nice little trick. If it is a positive, guess what? No matter if you have a positive or a odd, even or odd, if it's a positive leading coefficient, the right side goes up. Positive leading coefficient, the right side goes up. Every single time. Let me grab my yellow. Negative leading coefficient, what happens? What happens to the right side? It goes down. Right side goes down. Negative goes down. Negative, sad face, goes down. Now what about, you're asking, okay, well that tells us the right in behavior, but what about the left in behavior? The left in behavior is dictated by whether you have a positive and if it's an even or odd. Even, they have the same in behavior, right? Both sides go up or both sides go down. Odd, they do opposites. So let's look at example 1 and figure out what matches with what. So what I'm going to do is I'm actually going to take a break and actually no, you should probably pause it. Just pause the video, try to match up what goes with what. And what I'm going to do is I'm going to highlight. Is it a positive? I'm going to highlight all of the leading coefficients. So I'm going to look at each one of these. My leading term here is my highest power, x to the fourth, x cubed. So my leading coefficient is this 3. And I noticed that he's positive. That's why I used orange, because I knew he was going to be positive. And then I'm going to look at my next one. X cubed, x squared, x, my highest power is x cubed. So my leading coefficient, that is Kevin, and he's trying to entertain baby the best way he can. And that is why we're going to stop this video. Kevin! Kevin! Hush! My God. So I highlight what's positive, what's negative. What's positive, what's negative. And you're looking for your highest power. Because you're looking for your leading coefficient. Now, once you determine if it's positive or negative, the next thing you determine, so that will tell you whether it's going up or down. So then you can go with your same highlighter, highlight it going up on the right-hand side. If it's going up on the right-hand side, up on the right-hand side. So just by doing that, I know that part A is either capital A or it's capital D. Now I know that since A is an even x to the even power, I know both sides, both ends are going to go either up or down. Since it's positive, I know both sides are going to go up. So this little a matches with this capital D. So I will stop the video now. You try to finish this, and then we'll go over the rest of it. In the meantime, I have to go wrangle my 3-year-old who currently does not have a diaper, my little baby who, oh my goodness, but yeah. So